The first creature on our list is Hallucigenia, and its name tells you everything about first impressions. In 1977, paleontologist Simon Conway Morris gave it that name because it had, in his words, a bizarre, dreamlike quality. The animal itself was tiny, just half a centimeter to about 3.5 centimeters long, smaller than your thumbnail in most cases. But its anatomy launched a scientific argument that lasted 4 decades. For 40 years after its initial description, researchers reconstructed Hallucigenia inverted. They believed its rigid defensive spines were walking legs and that its actual legs were some kind of dorsal tentacles. The tail was mistaken for the head. It was by almost every measure built wrong on paper. The corrected anatomy, confirmed through increasingly advanced imaging techniques, reveals an animal that walked on 7 to 8 pairs of fleshy appendages called lobopods, essentially tentacle-like legs ending in tiny claws. The rigid spines were dorsal armor, pointing upward as protection against predators. The actual head is a small, elongated bulb equipped with simple eyes. 3 pairs of smaller, more delicate tentacles near the head were likely used for manipulating food. And then, in 2015, electron microscopy delivered a detail no one had anticipated. A mouth and throat lined with needle-like teeth, arranged in a ring, generating suction to pull a food inward. Hallucigenia was a benthic dweller living on the seafloor of what is now the Burgess Shale Formation in the Canadian Rockies, roughly 508 million years ago. It likely scraped along surfaces with its claws, feeding on sponges and organic debris. Its gut was a simple straight tube, often preserved in fossils as a thin, dark carbon line. One of the most telling anatomical details is the structure of its claws, which show a cone-in-cone composition. That specific trait is shared with modern velvet worms, also known as onisophorans, and it is one of the strongest pieces of evidence placing Hallucigenia in the evolutionary story. On the mainstream scientific view, Hallucigenia is a stem group lobopodian, meaning it sits on the evolutionary branch that eventually leads from simple worms to the complex jointed-legged arthropods, the group that includes insects, crustaceans, and arachnids. That makes this tiny, spiny creature a bridge organism between two of the most significant animal groups on Earth. A second perspective, raised by historians of paleontology and some working researchers, takes a different angle. The fact that Hallucigenia was reconstructed incorrectly for 4 decades suggests that our interpretive frameworks for Cambrian fauna may still be fundamentally flawed. If we got this one so wrong, how many other organisms from the same period are sitting in museums reconstructed backward or inside out? A third, more speculative line of thinking argues that creatures like Hallucigenia represent such radical departures from anything that came before that standard Darwinian gradualism. The idea of slow, incremental change struggles to explain their sudden appearance during the Cambrian explosion. Proponents of this view point to alternative mechanisms, from punctuated equilibrium to more radical models of evolutionary change. Hallucigenia's fossils are primarily limited to the Canadian Rockies, with a few specimens from China. And they are among the most famous examples of soft tissue preservation in what geologists call Lagerstätten sites, locations where conditions were perfect for capturing delicate biological detail. When you look at the fossil, it appears as a flattened impression in dark shale, almost like a sketch made by the rock itself. Now, if Hallucigenia looked alien enough to confuse scientists for 40 years, the next creature was so bizarre that when it was presented to a room full of experts, they could not stop laughing. The second creature is Opabinia, and its public debut is one of the most famous moments in the history of paleontology. In 1972, researcher Harry Whittington stood before an audience at a paleontology conference and presented his reconstruction of this Cambrian animal. The room burst into laughter. Not because the science was bad, but because the animal looked too absurd to be real. Opabinia had 5 stalked compound eyes mounted on top of its head, giving it near 360-degree vision. Extending from the front of its body was a long, flexible proboscis ending in a spiny pincer, essentially a biological vacuum hose. And here is where it gets truly strange. Its mouth faced backward, positioned on the underside of its head, which means its digestive tract had to make a U-turn inside its own skull just to connect. Despite all this complexity, Opabinia was only about 2 to 3 inches long, roughly 5 to 7 centimeters. It swam using 15 pairs of overlapping lateral lobes, essentially body flaps that rippled in sequence. 3 pairs of tail blades formed a V-shaped fan at the rear, used for steering and braking. Gills sat on the upper surface of those body flaps, maximizing oxygen intake during locomotion. Its feeding behavior was methodical. The trunk probed the seafloor, scooping up soft-bodied worms and organic debris, then passed the food backward to the mouth. Opabinia lived roughly 505 million years ago in the deep water sediments of the Burgess Shale, and like Hallucigenia, its body was covered by a soft, unmineralized cuticle with no hard shell, making fossilization exceptionally rare. The mainstream classification places Opabinia as a stem group arthropod, one of many evolutionary experiments during the Cambrian, most of which went extinct. But a second reading of the evidence points out that Opabinia's 5-eye visual system and complex feeding apparatus suggests that Cambrian ecosystems were far more ecologically advanced than scientists traditionally assumed. These were not primitive, simple creatures fumbling through existence. They were highly specialized. A third, more provocative interpretation uses the sheer disparity of Cambrian body plans like Opabinia as evidence against gradualism entirely, arguing instead for punctuated equilibrium or even saltational models where major evolutionary leaps happen rapidly. Despite all the alien-looking features, Opabinia maintained bilateral symmetry, just like you and me. It remains one of the most cited examples of morphological disparity, where the range of body shapes far exceeds what you would expect from the number of species. From tiny bizarre creatures in the Cambrian Sea, we now jump forward about 50 million years to something much, much larger. The third creature is Wiwaxia, and if the Cambrian had a punk rock scene, this is what the lead singer would look like. Picture a spiky armored blob, roughly 1 to 2 inches long, covered in overlapping scales with 2 rows of tall defensive spines jutting upward from its back. Those scales, called sclerites, numbered in the hundreds on an adult specimen, and they were mineralized, forming a kind of chainmail over the animal's upper body. The spines above them likely served as deterrents against Anomalocaris, the top predator of the Cambrian seas. Underneath all that armor, Wiwaxia crept along the seafloor on a muscular foot, very much like a modern slug. It fed using a radula, a scraping organ with 2 rows of teeth that ground up algae and microbial mats. It was bilaterally symmetrical, but its soft, vulnerable underside was completely unprotected. The armor only worked from above. Fossil evidence suggests that Wiwaxia shed its entire armor set at once to grow, leaving it temporarily defenseless during molting. It lived around 505 million years ago, a contemporary of Opabinia, and its fossils are often found flattened in shale, the scales sometimes showing a metallic or pearlescent sheen. The classification debate around Wiwaxia has persisted for decades. The mainstream position places it as a stem group Lophotrochozoan, belonging to the broad superphylum that contains both mollusks and annelid worms. A second perspective argues that creatures like Wiwaxia, which straddle major phylum boundaries, reveal that our classification systems impose artificial divisions on what was actually a continuum of Cambrian body plans. A third hypothesis, sometimes called the Halkyride connection, links Wiwaxia to other armored Cambrian organisms and proposes a now lost armored worm phylum that was far more diverse than the fossil record reveals. Wiwaxia lacked a defined head with eyes. Paleontologists distinguish front from back primarily by the orientation of the spines. It was highly susceptible to ocean chemistry changes, and specimens have been recovered from Canada, Utah, and China. Like so many Cambrian organisms, it appeared persisted for a while and vanished without descendants. But if these first 3 creatures show us evolution working at the miniature scale, our next entry operated at an entirely different magnitude. The fourth creature is Cameroceras, and the simplest way to describe it is this. Imagine a squid living inside a rocket shell. Cameroceras was a giant cephalopod with a straight conical orthocone shell, and it stretched over 20 feet long, with some estimates going higher. It dominated the oceans roughly 470 million years ago during the Ordovician period, making it the largest predator of its era. The shell itself was an engineering marvel. Divided into gas-filled chambers, it functioned as a buoyancy control system. Running through all those chambers was a structure called the siphuncle, a tube that allowed the animal to adjust gas levels and control its vertical position in the water column. At the business end, Cameroceras had a robust parrot-like beak and several tentacles for grabbing and crushing prey, including trilobites and early sea scorpions. It moved by jet propulsion, squirting water through a siphon, though it was likely a slow-moving ambush predator given the massive, inflexible shell limiting maneuverability. Its shell was composed of aragonite and calcium carbonate, essentially impenetrable to any predator alive at the time. The closest modern relative is the nautilus, which uses the same chambered shell buoyancy system, but at a fraction of the size. Mainstream science views Cameroceras as the peak of orthocone cephalopod evolution, the apex before more agile predators eventually displaced the straight-shelled forms. A second interpretation notes that the rarity of complete 20-foot specimens, since most fossils are partial shell sections, means size estimates could be significantly off in either direction, and our entire picture of Ordovician food webs depends on fragmentary evidence. A third, more speculative view extrapolates from shell fragment scaling ratios and proposes that the largest orthocones may have reached 30 feet or more, rivaling the modern giant squid. Shell fragments have been found across North America, Europe, and China, and it hunted in the dim, deep Paleozoic waters using large, sophisticated eyes. From the ocean's top predator, we now turn to something far less intimidating, an animal that became famous not for being fearsome, but for looking permanently confused. The fifth creature is Sacabambaspis, and if you were on the internet in 2023, you probably saw its face. Three-dimensional reconstructions of this ancient jawless fish went viral because it appeared to have a blank, expressionless stare, two forward-facing eyes pressed close together, and a tiny, slit-like mouth that created what people immediately called a derpy, smiling face. It became a global meme almost overnight. But beneath the comedy is a genuinely important evolutionary story. Sacabambaspis was approximately 1 foot long, about 30 centimeters, and it lived roughly 450 million years ago during the Ordovician. Its head was encased in a bony shield composed of dorsal and ventral plates, and its tadpole-shaped body was covered in elongated chevron-shaped scales arranged in rows. Here's the anatomical paradox. Forward-facing eyes are typically a predator adaptation used for depth perception when chasing prey. But Sacabambaspis was a defenseless filter feeder, sucking small organic particles from water or sediment. It was a poor swimmer, moving in erratic bursts to escape predators like sea scorpions. Most articulated specimens come from the Anzaldo Formation in Bolivia, and they are often found in large death assemblages, clusters of many individuals preserved together, suggesting either shoaling behavior or mass mortality events. Despite its seemingly crude design, Sacabambaspis possessed a primitive lateral line system for detecting water vibrations and a relatively complex brain with distinct lobes, along with multiple gill openings on the sides of its head shield. The mainstream classification places it as an ostracoderm, one of the earliest known vertebrates with a complex dermal skeleton, representing a key evolutionary step toward all-jawed vertebrates, including us. A second interpretation looks at the Bolivian death assemblages and argues they point to a catastrophic environmental event, possibly volcanic activity or ocean anoxia, challenging the idea of gradual decline. A third, more speculative view uses Sacabambaspis' seemingly unrefined body plan to argue that early vertebrate evolution was far more chaotic than textbooks suggest, more like random assembly than adaptive refinement. Regardless of which interpretation you favor, here is the takeaway. When you look at that goofy, meme-worthy face, you are looking at one of your own earliest relatives. From the water and from creatures measured in centimeters, we now move to the land, forward about 100 million years, to something measured in meters. The sixth creature, and arguably the most dramatic terrestrial arthropod in Earth's history, is Arthropleura. Before anyone knew what it was, they found its footprints. Massive trail impressions were discovered across 3 continents, in Canada, Scotland, and Germany, and for decades, researchers attributed them to giant amphibians. No one believed an invertebrate could grow that large. They were wrong. Arthropleura was a millipede-like creature that exceeded 8.5 feet in length, nearly 2 feet in width, and weighed an estimated 110 pounds based on technical biomechanical models. It flourished during the Carboniferous period, roughly 345 to 290 million years ago. The key to its size was the atmosphere. During the Carboniferous, oxygen levels reached approximately 35%, compared to today's 21%. Arthropods breathe through tracheal systems, networks of tubes that deliver oxygen directly to tissues. The maximum size an arthropod can reach is physically limited by how far oxygen can diffuse through those tubes. At 35% atmospheric oxygen, proportionally larger tracheal networks became viable, and gigantism followed. Arthropleura's body consisted of roughly 30 jointed segments protected by side plates called paratergites, with dorsal plates covered in small tubercles and spines. Its dozens of pairs of legs, each 5 to 8 inches long, distributed its considerable weight across the forest floor in a stable but slow crawling gait. Despite its intimidating size, fossilized gut contents reveal it was likely a detritivore, eating rotting plant matter and spores, not a predator. It lacked powerful mandibles and relied on its armored shell for defense. It lived in the lush, humid coal swamps and equatorial forests of the supercontinent Euramerica. In 2024, newly described fossil head specimens revealed stalked compound eyes similar to those of modern crabs, the first clear evidence of head anatomy for a creature that had been known since the 19th century. The mainstream oxygen gigantism hypothesis directly links Arthropleura's size to hyperoxic atmospheres. A second interpretation argues that oxygen alone is insufficient, that reduced predation pressure and abundant food were equally necessary cofactors. A third, more speculative idea proposes that Arthropleura may have been partially aquatic, semi-amphibious, which would change weight-bearing calculations and potentially allow for even larger sizes. It disappeared during the early Permian as the climate dried and oxygen levels plummeted. From the largest bug on land, we go to the largest bug in the water. The seventh creature is Jaekelopterus, the largest sea scorpion to ever exist, reaching 8.5 to 9 feet in length. Its armored chelicerae, the front claws, were nearly 1.5 feet long and lined with jagged spikes. It had no teeth at all. Instead, it used those spike-lined claws to snatch, crush, and dismember prey. If you have played the Fallout video game franchise, think of a real-life Mirelurk, and you are not far off. Jaekelopterus lived approximately 390 million years ago during the early Devonian, and despite the name sea scorpion, it occupied freshwater river systems and estuaries, not the deep ocean. It dominated its ecosystem, preying on early jawed fish called placoderms, and it weighed an estimated 450 pounds or more. Massive compound eyes gave it high visual acuity in murky freshwater, and a flattened paddle-like tail called a telson powered its propulsion. Like modern large arthropods, cannibalism was likely common, especially given resource competition. And like all arthropods, it was at its most vulnerable during molting, when it had to crawl out of its old exoskeleton to grow. Its gill tracts were located on the ventral side of the body, and its mouth sat on the underside between the legs, surrounded by spiny leg bases called gnathobases that ground food before ingestion. The most famous claw fossil was recovered from Prüm, Germany. The mainstream view holds that Jaekelopterus was an ambush predator capable of high-speed bursts that went extinct as larger, more agile-jawed fish outcompeted it. A second interpretation challenges the sea scorpion label entirely, arguing that Eurypterid ecology has been fundamentally mischaracterized and that these animals were primarily riverine and estuarine, not marine. A third hypothesis speculates that Eurypterids like Jaekelopterus may have been capable of brief terrestrial excursions similar to modern horseshoe crabs, given their limb structure and gill tract design. From an arthropod that looked like a nightmare, we move to a mammal that looked like it was assembled from spare parts. The eighth creature is Chalicotherium, and the best way to picture it is as a biological mashup of a horse, a gorilla, and a giant ground sloth. It walked on its front knuckles like a gorilla to protect massive curved claws. Its front arms were oddly elongated while its hind legs were shorter and stouter. And here's the classification shock. Chalicotherium was an odd-toed ungulate, a perissodactyl, making it a direct relative of modern horses and rhinoceroses. It lived from the late Oligocene to the early Pliocene, roughly 28 to 3.6 million years ago, and stood approximately 8 to 9 feet tall at the shoulder, weighing up to 3,300 pounds. It was a high browser, using those long arms to pull tree branches down to its mouth and stripping leaves with a muscular tongue and soft lips. It lacked front teeth in its upper jaw entirely and had low-crowned molars adapted for soft forest vegetation, not abrasive grasses. Thickened callosities on its sitting bones allowed it to sit on its haunches for extended feeding periods, and its claws were not weapons for hunting, but tools for raking vegetation and defensive slashing against predators like the bear dogs of the era. The initial discovery was a mess. Paleontologists classified the claws as belonging to a giant pangolin and the teeth as belonging to a horse, as if the animal could not possibly exist as a single organism. Mainstream science classifies Chalicotherium as a convergent evolution case study, an animal that filled a niche similar to ground sloths or gorillas through entirely independent evolutionary pathways. A second interpretation focuses on its global range across Europe, Asia, and Africa, arguing that its total extinction coincides with a catastrophic ecological shift as forests gave way to grasslands, a transition far more devastating to woodland megafauna than previously appreciated. A third, more speculative line connects the extreme body plan to forest giant folklore in Eurasian traditions, a cryptozoological hypothesis with zero scientific support but some cultural resonance. Bone analysis reveals slow growth rates and relatively long lifespans, and its preferred habitat was moist, closed canopy forest. The entire family Chalicotheridae left no living descendants. From a misidentified mammal, we move to a misidentified reptile. The ninth creature is Postosuchus, and it has been living under a false identity for decades. Frequently mistaken for a dinosaur, Postosuchus was actually a Wiwaxia, a member of the crocodile line Archosaurs, making it more closely related to modern crocodiles than to any dinosaur. It stretched up to 13 to 15 feet in length, weighed between 550 and 660 pounds, and was the dominant super predator of late Triassic North America, roughly 221 to 202 million years ago. It could sprint on its hind legs when attacking prey, a trait it evolved completely independently from dinosaurs. Its skull was massive, nearly 1/3 the length of the entire body, narrow but very deep, with enormous jaw muscle attachment areas. Its teeth were large, serrated, and dagger-like, designed for bone-crushing bites, and rows of thick bony osteoderms protected its back. Unlike modern crocodilians, which sprawl with legs splayed to the sides, Postosuchus held its limbs tucked directly under its body in an upright stance. It was a generalist carnivore that preyed on early dinosaurs and on its own crocodile line relatives. Its forelimbs were roughly 60% of its hind limb length, equipped with large hooked claws, and a long, heavy tail served as a counterbalance for its massive head during bipedal movement. Fossils come primarily from post-quarry in Texas and the petrified forest in Arizona. The mainstream interpretation frames Postosuchus as the ultimate example of convergent evolution in action, what some researchers informally call the dinosaur scam. Upright gait and bipedalism are not unique dinosaur innovations. They are general adaptations for cursorial predation that evolved multiple times independently. A second interpretation reframes the entire Triassic as a competitive battleground between the crocodile line and dinosaur line Archosaurs, arguing that Postosuchus's dominance proves dinosaurs were not inherently superior, but won their position through the luck of an extinction event. A third hypothesis questions whether Wiwaxians might have had more advanced thermoregulation than currently recognized, potentially warm-blooded like dinosaurs, which would fundamentally rewrite Triassic ecology. Postosuchus was wiped out during the Triassic-Jurassic extinction event roughly 201 million years ago, clearing the ecological space that dinosaurs would fill for the next 135 million years. From the Triassic, we leap forward to the Pleistocene, and a creature that baffled Charles Darwin himself. The 10th and final creature is Macrauchenia, and its story begins in 1834 when a young Charles Darwin found its remains in Patagonia and was, by his own account, completely baffled. It had the body of a camel, the three-toed feet of a rhinoceros, and its nostrils were not on its snout but high on its forehead, between the eyes. The skull structure strongly suggests a short, muscular trunk similar to a sagey, antelope, or tapir. It was approximately 10 feet long, weighed about 2,200 pounds, and belonged to the extinct order Jaekelopterus, a group of South American ungulates with no modern descendants. For over a century, no one could figure out where Macrauchenia fit in the mammalian family tree. Then, genetic analysis provided the answer. It was a distant relative of perissodactyls, the group containing horses and rhinos. Macrauchenia survived until roughly 10 to 12,000 years ago, at the very end of the Pleistocene, making it one of the most recent creatures on this list. It had long lower limbs and specialized ankle joints that allowed highly agile running with sharp turns, likely a defense against predators. Its herbivorous diet probably involved using that trunk to strip leaves from thorny bushes, and it retained a full set of 44 teeth, a rare holdover of the primitive mammalian tooth count. In modern terms, that is like finding a smartphone with a rotary dial still built in. The mainstream interpretation frames Macrauchenia as a textbook example of convergent evolution, an animal that independently evolved a camel-like form due to similar ecological pressures on South American grasslands. A second interpretation points to a perfect storm of extinction causes: climate change, the Great American Biotic Interchange, where North American species flooded southward after the Isthmus of Panama formed, and early human hunting, all converging within a narrow window. A third, more speculative hypothesis suggests that isolated populations may have survived longer than the fossil record indicates, given the vastness and poor paleontological sampling of Patagonia, a hypothesis with no supporting evidence, but one that cannot be technically disproven. Key fossil material comes from the Luján Formation in Argentina. Darwin could not have placed this animal genetically. It took nearly 2 centuries, and the maturation of DNA extraction technology to connect Macrauchenia to the horse and rhino lineage. Now that we have covered creatures spanning from 508 million years ago to 10,000 years ago, it is worth pulling together a thread that connects 3 of our largest entries. Arthropleura at 8.5 feet on land, Jaekelopterus at 9 feet in water, and Cameroceras at over 20 feet in the ocean all achieve sizes that are physically impossible today. The reason comes down to one variable: oxygen. Arthropods breathe through tracheal systems where oxygen diffuses directly through tubes to reach tissues. The farther oxygen has to travel, the less efficiently it arrives. At today's 21% atmospheric oxygen, the largest terrestrial arthropod is the coconut crab, with a leg span of about 3 feet. During the Carboniferous, Piker's atmospheric oxygen reached roughly 35%, a 67% increase, and proportionally larger tracheal networks became viable. The mechanism behind that oxygen spike was the Carboniferous coal swamps themselves. Massive forests produced enormous quantities of oxygen while simultaneously burying carbon in sediments, preventing it from re-entering the atmosphere. When those conditions collapsed during the Permian, oxygen levels crashed and Arthropleura disappeared with them. Cephalopods like Cameroceras used gills rather than tracheal tubes, but they still benefited from higher dissolved oxygen concentrations in seawater. Jaekelopterus occupied an interesting middle ground with its ventral gill tracts, a hybrid system suited to its freshwater habitat. The mainstream oxygen gigantism hypothesis is well established in the literature. A second interpretation argues that oxygen was necessary but not sufficient, that ecological factors like the absence of large predators and abundance of food were co-equal drivers, and that popular science overemphasizes the oxygen narrative. A third view proposes that ancient arthropods may have had fundamentally different respiratory physiology, not just scaled-up versions of modern systems, but entirely different architectures that allowed size thresholds we cannot predict from living analogs. This connects to modern astrobiology. When scientists model the conditions needed for complex alien life, atmospheric oxygen concentration is one of the first variables they consider. Buoyancy also matters. Cameroceras' shell essentially eliminated weight constraints, allowing it to reach sizes that no land animal with the same body plan could achieve. Arthropleura at 110 pounds versus Jaekelopterus at 450 pounds illustrates the aquatic size advantage clearly. Meanwhile, Hallucigenia, Opabinia, and Wiwaxia all remain tiny despite available oxygen. Gigantism was an option, not a requirement. Here is a pattern worth noticing. At least 5 creatures in this video were fundamentally misunderstood for years or decades after discovery. Hallucigenia was upside down for 40 years. Arthropleura's trackways were attributed to giant amphibians because no one believed an invertebrate could grow that large. Chalicotherium's claws were classified under pangolins and its teeth under horses, as if the animal could not possibly be a single organism. Postosuchus was automatically labeled a dinosaur because its body plan matched existing preconceptions. Sacabambaspis' forward-facing eyes were initially read as a predator trait when the animal was actually a harmless filter feeder because our interpretive frameworks carry modern ecological assumptions. This is not random error. It is cognitive anchoring bias, the unconscious tendency to force new data into existing frameworks rather than creating new categories. Most fossils are fragments, and reconstruction inherently involves assumption. Cameroceras' size estimates vary enormously precisely because most fossils are partial shell sections. The mainstream view treats these misidentifications as a normal, self-correcting feature of science. New techniques like CT scanning, electron microscopy, and ancient DNA analysis continuously improve our understanding. A second interpretation sees a systematic pattern. We consistently underestimate invertebrate complexity and overestimate vertebrate and dinosaur dominance because of a cultural fascination with big predators. A third, more philosophical critique argues that if we got Hallucigenia wrong for 40 years, the proportion of currently accepted reconstructions that are fundamentally incorrect could be far higher than the field acknowledges. Consider that the 2024 Arthropleura head discovery, revealing stalked compound eyes, confirmed a basic anatomical feature for a creature known since the 19th century. Or that Macrauchenia's genetic relationship to horses was not confirmed until DNA technology matured, something Darwin could not have known. Or that the Opabinia laughter incident at that 1972 conference illustrates something about the social psychology of scientific consensus, how absurd-looking truths get rejected. Wiwaxia's classification as mollusk or a worm remains unresolved to this day. The broader point is worth sitting with. Our image of the ancient world is always a reconstruction, never a photograph, and new discoveries from Lagerstätten sites could overturn current models at any time. So what does all of this mean for how we think about life on Earth? None of these creatures were ugly in their own time. Every spine, claw, proboscis, and armored plate was a survival solution refined over millions of years. Wiwaxia's armor, Hallucigenia's spines, and Arthropleura's exoskeleton represent three completely independent solutions to the same fundamental problem: do not get eaten. Convergent evolution appeared repeatedly in our list. Macrauchenia evolved a camel-like form independently of true camels. Postosuchus evolved a dinosaur-like posture independently of actual dinosaurs. Chalicotherium evolved gorilla-like locomotion despite being related to horses. Evolution explores morphological possibilities the way an engineer explores prototypes, and the Cambrian explosion was the most prolific prototyping phase in Earth's history. Of the 10 creatures we covered, most left no descendants. Entire lineages erased, and contingency played an enormous role. If the Triassic-Jurassic extinction had not killed Postosuchus and its Rauisuchian relatives, crocodile-line archosaurs might have remained apex predators, and dinosaurs might have stayed marginal. Stephen Jay Gould's famous thought experiment captures this perfectly. If you could rewind the tape of life and play it again, you would get a completely different cast of characters. Cameroceras used jet propulsion inside a rigid shell. Modern squid used jet propulsion with flexible bodies. Evolution kept the engine and redesigned the chassis. The mainstream view holds that natural selection acting on random variation drives it all, and designs that work persist regardless of aesthetics, while beautiful ones that fail get eliminated. A second interpretation suggests the sheer number of failed body plans from the Cambrian points to a period of relaxed selection, not intensified adaptation. A third perspective from complexity science argues that self-organization and developmental constraints play a larger role than selection in producing body plans, that evolution is less design and more crystallization. Every extinction event reshuffled the deck, removing incumbent designs and opening space for new ones. Sacabambaspis, despite its comedic appearance, represents the vertebrate lineage. Our lineage. Macrauchenia's extinction just 10,000 years ago means we share a timeline with some of these seemingly impossible creatures. And if we got Hallucigenia upside down for 40 years, What else might we be getting wrong right now? Nature does not care about aesthetics. It never has. 500 million years of experimentation produced everything from half-centimeter spiny worms to 20-foot rocket-shelled predators, and the creatures we would call the ugliest were often the most successful organisms of their era. Ugly is our judgment. Survival is nature's. The fundamental laws of physics, chemistry, and atmospheric composition set the boundaries, oxygen levels, ocean chemistry, continental configurations, and life fills every available space within those boundaries. Every creature in this video solved the same three problems: eat, avoid being eaten, reproduce. The next Burgess Shale discovery could reveal something even stranger than Opabinia or Hallucigenia, and it probably will. Nature's only aesthetic is function, and its only rule is, does it work?